Hi, my name's Dave, amateur radio call sign AB7E, and I have a tower with a couple of antennas on it, a couple of Yagis, and they are turned by a heavy-duty rotator. That the rotator works fine, but the controller for it has pretty much stopped working, at least properly. Now I can turn the rotator very easily with just a DC power supply and a PWM controller to ramp the speed up and down, but trying to determine which direction the antennas are pointed is a little bit more difficult. Some time ago I worked up a video showing a magnetically linked rotator indicator, rotation indicator, and that has worked reasonably well for me over the last year or so. But it's got some amount of friction in it, and it causes the indication to lurch. It'll stop, it'll pause, and then jump 10 to 12 degrees all at once. And I got tired of that, so decided to go with a more direct mechanical linkage using a toothed belt like this and suitable geared pull or tooth pulleys, one for the mast and one for the indicator. Now, the whole idea is based upon this little job. This is a Hall effect rotation sensor, and the shaft continuously turns. There is provision for 5 volts going to it, or it's designed to run on 5 volts DC. And if you put 5 volts DC on it, this wire, then this wire here will read between 0 and 5 volts relative to ground, depending upon which position the shaft is in. So 0 to 360 degrees rotation of the shaft correlates or translates to 0 to 5 volts on this lead here. This is a nice little encoder. It uses 2 Hall effect sensors, 2 Hall effect units inside. It uses 2 Hall effect sensors inside driving an integrated circuit. The Hall effect sensors are at 90 degrees to each other physically, and the IC translates the relative indication off the Hall effect sensors to an angular rotation of the shaft. These run about $27 on Amazon, and they come with this little plate here. Come with that. So this is the heart of the system. And then I have these 3D printed parts. Now I already have a setup like this up on the tower, and it's worked very well. And I printed those in a black PETG, but black's pretty hard to see. I was pretty sure that you wouldn't be able to see much detail in this video with the black. It's shiny, and so I picked the ugliest color that I have in my setup and printed these in this purple. The design for the toothed, or the model I should say, for the tooth pulley here comes from a design that was worked up probably, I think it was back in 2012. It was done up in a free modeling program called OpenSCAD, and it's parametric, meaning that that model is, meaning that you can change just about any dimension on this to suit your particular needs. You can change the thickness, you can change the number of teeth. There's a recess for this flange. The flange looks like this. It's got a hole for a 6mm shaft. The encoder has a 6mm shaft. So all of that is adjustable, parametric. Now if you've got the patience to, or the inclination to see how I did that, at the end of this video I'll run through the OpenSCAD model and show the changes I made to the original to get to this, and also to come up with this toothed collar. This is the part that goes around the mast, and I made it just slightly larger than the mast so that I could put a compressible rubber shim so that when I clamp this around the mast, it's physically locked in place. It won't slide. Now, in the model that I worked up, this is my adaptation of this, and I put these holes in here. They're for alignment, and I made some pins out of nothing more than finishing screws or finishing nails, and they go in here like this. And this is so that when you're up on the tower trying to put this in place on the mast, it provides a positive alignment. Clips in like that. Now it's pretty solid. And then you use a couple of hose clamps to tighten it down and keep it in place. So there's that. This, of course, goes on the rotation encoder, and there's a set screw here to lock it in place. So as this turns, so will this shaft. To hold all of this, I designed this up, this is my design, for a bracket that would hold the rotation indicator, encoder, and that goes in here something like that. Screws down with a couple of screws, locks it in place, and I'm going to take this back out. My tower has 3 plates up there near the top of the tower. One is the rotator plate to hold the rotator. The top plate holds a alignment bearing to keep the shaft or the mast from swinging from side to side. But then there's a middle plate in between those 2 plates that the mast goes through a hole in it, and that's what this plate, this steel plate here, is simulating, because as the mast goes through this plate, I'll lock this in place on the mast, and then this will hold this bracket will hold this encoder, but I need to be able to adjust this for position to tighten up the belt, but I need it to stay in place once I adjust it. So my solution for that is to use these rare earth magnets. They're very strong. These are 1/2 inch diameter and about 1/4 of an inch thick, and they go on here, or in these recesses, if I can get them in right, and I almost never do. But this you would take up on the tower and put these all in place up on the tower. Now once I have this all set up like this, this is movable, but it takes a fair amount of force to do it. So I would have this on here, would put this on top of that, set the set screw, have this in place, and then slide that back to tighten up the tooth belt like that. Okay, I'm going to show you how I read the output of this. If you give me just a couple of minutes, I'll come back and have this wired up. I feed the output voltage from this to nothing more than this 3-terminal voltmeter. This is literally a voltmeter. You put 12 volts on here, and then this will read the voltage that is on this white lead. So you really only need 3 wires going from your ham radio room up to the tower. The same 5 volts that goes up to the encoder can be used to power up the voltmeter, and then you just essentially connect these two, and this will read out the azimuth of the antennas as a 0 to 5 volts here. Now, normally you would probably take that 0 to 5 volts and use something like an Arduino or whatever to convert that to 0 to 360 degrees. But I found I really didn't need that. It's just as easy to think in terms of volts for azimuth as it is for degrees. I use a great circle chart, and I have superimposed the voltages for my particular setup onto that great circle chart, and I've come to think in terms of the volts when I'm trying to decide which way to point the antennas. From southern Arizona here, if I want to point towards Europe, that's normally about 30 degrees, and I just point to 2.5 volts on here. Africa is about, maybe 3 volts or somewhere in that range. Japan is about 1.5 volts. And I'll show you here the great circle chart with those voltages superimposed on it. It's very simple and easy to use. Okay, I'm going to power this up and show you that as I rotate this, the indication changes. Okay, I've haywired this up. It's quite a rat's nest here of wires, but it's really very simple. It's just 5 volts from a supply that I have off to my left here. There's a 5 volt supply that goes to the encoder. Same 5 volts feeds this 3-terminal voltmeter. These, by the way, are only around, I don't know, $4 or $3 or something like that. They're quite cheap on Amazon. And if you don't have a 5 volt power supply, something like this will do the job for you. I bought 10 of these for $12 total. These are little buck power converters, voltage converters. And you can set this with this little trim pot here. You can set that to 5 volts, and you could feed it with almost any old wall wart, any DC wall wart, 9 volt, 12 volt, whatever you have left over. I never throw wall warts away, and so it's a cheap way to make a 5 volt supply. Okay, so here's the 3-terminal voltmeter. I put this little diffusion plate on top of it. By the naked eye, it's real easy to read. These digits are very bright, but I noticed that on the camera they kind of overpower it, so I'm hoping that this diffusion plate will kind of address that so you can see the digits better. Now as I rotate the encoder, you can see the voltage increasing. And when it gets to 5 volts, it'll flip over. There we go. So these encoders, the Hall effect encoders, they're rated for something better than I think, well, in the vicinity of a degree of accuracy. So it's certainly good enough for pointing an antenna that is going to have a much wider beam width than that anyway. Even with my Yagis, I've got an 8-element Yagi on 10 meters, and you wouldn't be able to pick out a degree of azimuth change. Okay, so in my case, I didn't want to take the mast and antennas out of the rotator. The combined weight of those is something up around, I don't know, 300 pounds. So which means I have to drag a winch that I've made up to the tower, hook it to the mast, pull it up, get it out of the rotator so that I would normally be able to put the belt in and then drop it back down. So what I did is I cut the belt. I cut it before I went up on the tower, and then once I was on the tower, I glued it back together. Now that sounds pretty dicey, but believe me, it is a secure way to do this. And I'm going to show you that here. Let me put some of this stuff aside and I'll come back and show you how I do that. Okay, I have here a piece of a belt that I had experimented on before. I'm going to use that to show you how I can make a splice. These belts are available on Amazon as well. But by the way, all this stuff, the flange, the little buck power supply, the rotation indicator, all that's available on Amazon. And no, I don't own any stock in them. So you can take, like I said, I would normally cut this ahead of time before going up on a tower. There's no point in cutting it up on the tower. But you want to make a single, as best you can anyway, single clean cut all the way through it. And I didn't quite get it all the way through, but let's make sure I'm in the same cut. Okay. So we're going to use super glue to glue this back together. Now super glue is has what's known as a hydraulic cure, which means it sucks moisture out of the air to cure. There's a lot of things that do that. Silicone rubber, polyurethane foam, they all use a moisture cure. I actually brought up to the tower some water to facilitate that, and we'll do the same thing here. I guess I can leave that open. So take the super glue, put a thin coat on the edge, set that down, and then it works best to do it from the back side. Match that up, and then to start with, I just breathe on it. I use the moisture in my breath to help set it. Some of you live in wetter climates than Arizona, probably don't need to do this at all. Okay, I think that's sort of set. I'm going to put that down on there, put my knife on it to hold it down. And then to reinforce the splice, I have a piece of polyester fabric. The fibers themselves are quite non-stretch. Turns out that, according to the internet anyway, cotton of a normal weave and linen, they're also quite non-stretch. So I'm going to take and put a layer of super glue on the back side, obviously, of the splice. We'll try to drop this on here without getting it all over my fingers. Tap it down, and then we'll saturate it with some more super glue. Hope you can see this. Now if you want a nice pretty joint, just let that sit for however long it takes to cure up properly. But if you're in a hurry, you can take and dab a little bit of water on it, and it will greatly facilitate the cure. The only thing is it kind of bubbles up the surface and makes it look white. Now I'm going to let that set, but here's a piece that I had done before, and you can see how white and textured the surface becomes, but I cannot break that. So it's not going to break up on your tower either. Okay, that's how I get the indicator and everything set up on the tower. Hope you found some of that useful. If you happen to have a mast that is 2 inches in diameter or close to it, you could probably find a use for this and the other two pieces that I 3D printed. So I will put those, the STL files, I'll put a link to those in the text below this video. The files will be on a website called Printables that collects a lot of 3D printed files. So you'll be able to just download those STLs, either print them yourself or get somebody to print them for you, and hopefully pick a nicer color than I did here. And you'd be set to go for your own setup. If you don't have a 2-inch mast, if you have something that's either 1.5 or 3 inch or something like that, you would need to make this pulley bigger, this one bigger, and you'd have to make a few changes in the overall dimensions. So if you're in that situation and are willing to or interested in making your own, stay tuned, and I'll run through how I did these in OpenSCAD so that you could do the same thing except to your own dimensions. So thank you very much for watching this far, and stick around if you're interested in how to use OpenSCAD to customize it to your own installation. Thank you much. Okay, this is the OpenSCAD window with the toothed pulley as originally designed by the folks that are referenced up here. The original guy was Draft Arts back in January 2012. It's been updated by a bunch of people actually, but most recently I think by this fellow named Oscar, and he uploaded his version to thingiverse.com and also Prusa's website, printables.com. The code is actually pretty long. It's about 365 lines of code because it's parametric and it has lots of options. And I'm going to walk you through the options that converted this to what I used. This particular default pulley has 60 teeth. It's a GT2 profile, which means that the teeth are 2 millimeters apart. It's a fairly narrow pulley, and it has provision for this rather large flange. So the changes I made to it, first off, I'm going to come down here to line 25, and instead of 12, which is just a reference number, I'm going to change that to 14, because as you'll see here as I pan across, these are various options, 9, 10, 11, 12. 12 is for a GT2 profile, 2 millimeter spacing, but 14 over here at the end is for a 5 millimeter GT2 profile, but 5 millimeter spacing. So we go back here. So I've changed that to 14. Now when I hit the F5 key, it will reconfigure the drawing here. You won't be able to see me do that, but I'm going to just do it behind here. And then I need to resize it. Okay, so I've now made that a 5mm pitch on the teeth, which made, of course, the pulley a lot bigger. Now, to get around the 2-inch mast that I had, I needed 42 teeth. So here at line 24, we're going to change that to 42. Hit F5 again. And then this particular, the default configuration had an 8mm hole for the shaft. I'm going to change that to 6.2mm here at line 26 for a 6mm shaft. Hit F5 again, made the hole smaller. And I wanted a wider belt because the belts that I showed in the previous portion of this video are actually about 15mm wide. So over here where it says toothed part length at line 27, we're going to change 6.2 to 18. We'll give it a little bit more spacing around a 15mm. That makes the whole pulley wider. I wanted a bigger lip, top and bottom here. This looked a little flimsy to me. So down here in line 35 where it says retainer height, that was set to 1mm. I'm going to change that to 4mm. Made that bigger. And back up here at line 57, oh, I guess down, excuse me, line 57, I'm going to go 58 first. That's the flange diameter, line 58. That's this diameter of this recess here. And that was a pretty big flange. The flange that I referenced, that I used, are smaller than that. I'm going to change that to 24mm. Hit that again. And now we need to change the spacing between the holes for the flange. And we do that at line 57 here. I'll change that to 16 divided by 2, which is obviously 8mm, but the 16 is a convenient reminder of how big the flange is. Hit F5 again. And now that's the tooth pulley that I used for the encoder. Now, to make a toothed ring for the mast, I wanted to take this, make the edges here much wider so I could put the hose clamps on it. I wanted to make a large hole in the center for the 2-inch mast. I wanted to cut it in half and then put those holes for the pins. Now, trying to do that all in this version of the code got really messy. So instead of trying to do that, I ended up saving the model as it is right now to an STL file. First we're going to render it, which takes a little bit of time here. And by saving that STL file, I've locked in this model, period. And then I can re-enter that into a fresh instance of OpenSCAD and do whatever playing around I want with it. Every time I click on this, that image goes away, but it'll come back when the rendering is finished. So as soon as it stops rendering, we will save this or export it as a STL file, which is typically what you load into the slicer that gives the code for the 3D printer. And in fact, that's exactly what I did for the encoder. I just simply used that STL file in the slicer and then for the 3D printer. But now what, and by the way, I go up here to do the export, and that's export as STL. Now, I've already done that, so I'm not going to do it again, but I then, like I said, save this as an STL file. Now, if I go over here to another instance of OpenSCAD, and this is the code that I wrapped around that version here, this model, to do what I wanted to do for the ring for the mast. Now I'm in this other instance. I'm going to hit F5 and it will reconfigure the image here. And you can see that the yellow is the same toothed pulley that we just left. And I, with the code here in lines 10 through, well, first of all, line 8 is how I get that STL file back into OpenSCAD. And it's simply an import statement, and I have that right here on line 8. And then lines 10 through 18 10 through 18, yeah, 10 through 16. They add these two extra thicknesses of material, which is where the hose clamps would go. And then I'm going to come down here to line 20. I've commented that line out, but now I'm going to take the comments out. I'm going to hit F5 again, and that put a cylinder through the object. And when I use the difference command, which will subtract this cylinder from the rest of the model, it'll put that big hole there. And then to cut everything in half, I have a cube that's in line 20 through 24. I'll hit F5 again, and you'll see this big cube. So now when I use the difference command, which is currently commented out, it will subtract the cylinder, and it'll subtract half of the model. So I'm going to do that right now. Or take the commenting out of that, reinstate the difference command, and the image is weird. It makes it look like there's holes in the teeth, but they aren't really there. And the lines that are between 27 and 49, they are cylinders that I put in here, and then the difference subtracts those out and makes holes. So I think you can kind of see those. Now when I render this, it should show it better. And that's going to take some time again. Sorry I did that. Let's see if I can get it back. Yeah. So I created a half shell, and then when I printed them, I printed 2 of them. You can see, I think, the holes for the pins. You can see that there is indeed material here. They aren't holes between the teeth. And then I save this as an STL file, import that into the slicer, 3D print it. So that's probably pretty clumsy and confusing, but if you are interested in making your own version of this, like I said, OpenSCAD is free. It's an easy download, and by using that pre-built code and making the changes that I showed you, except with values that fit your particular need, you should be able to duplicate this process and come up with models that will match your mast and your setup. So, hope you found that somewhat interesting and not too boring. Thanks for watching.